Welcome back to the video lecture series for Introduction to Data Programming using Scala. In this video, we continue talking about linked lists, and in particular, I want to kind of go into the nature of linked lists and compare them to arrays. So we've been using arrays a lot, and we could actually write our sequence/list ADT using an array. So it's good to compare that, to have that in your mind for thinking about what we would do with a linked list. So this is the standard picture that we draw for an array. An array really is a contiguous chunk of memory in the computer. And if you are working in a language like C or C++, you would have a much more direct access to the memory itself. In fact, in C, an array is just a pointer to one piece of memory, and all of the pieces are the same size, so you can figure out where any other piece is just by doing a little math. You take the location of the first one and you add to it however many you want to move down multiplied by the size of each one, and that can give you this. So arrays have very fast random access, the ability to go to any single element. You can just do that automatically with an array. Now, it's worth asking ourselves, how would we implement our sequence ADT if we were doing it in an array? So we want to implement these methods here. And normally the way that we would do this, let's go back, I'm going to make it so this is a mutable list. So if I were to do this, new Scala class, array list of A extends my list of A, and I would need to make it so that my type A has a manifest, and I'm going to start off with, I'm going to make this a var. The data itself, I don't know, we'll say we have, A 10 elements to start off with. Now that might not be the size of our array. So when we start off, our list is empty, and we have an array that's bigger than that. Some of these methods then are very easy to implement. For example, getting an element out, we just index into the array. Like I said, very simple and straightforward. The is empty. Num elms equals 0. Size, well, that's what this is. Adding and removing are a little bit harder, and I won't actually write these, but I just want you to think a little bit about how they're going to work. That should probably make the code happy. So what happens when I have some values in this array? And so let's say I had added stuff, so I had 5 elements in here. It has a capacity of 10, and if I try to add things beyond the capacity, I would have to make a bigger array, just like what we did with our stack and our queue in the last chapter. But let's say I want to add something at index 1, and I have 5 elements in here. Well, what do I have to do? I can't just stick something in here because it will overwrite this value. So I actually have to copy values down, and then that makes room for me to put something in. So that's what my add method would have to do. Similarly, my remove method, if I wanted to remove this element, would have to copy elements back. And so it turns out that when we write our list ADT using an array, the get method, the apply, the random access is very fast. And it's very fast because all that's happening on the computer is literally just take the address of the first location, add to it index times however big the locations are, and boom, you have the memory that you want to access. However, adding and removing require lots of copying things around. They require order in copying things around. Remember with our stack and our queue, we said hard rule, everything has to be order 1. We can't do that with a list. It's impossible for us to write these general functions and have all of them be order 1. So you kind of have to pick which ones are going to be expensive and which ones are going to be cheap. And in the case of an array, the apply method, the getting an element, is cheap and fast. But adding and removing are, and by cheap and fast, I mean order 1. So these 3 methods down here are all order 1. Add and remove, however, are order in, and they're order in how many memory moves you have to do. So we have to change order in memory. And that's significant because turns out changing memory is slower than just accessing memory. And so it's better to have order in memory accesses with order 1 memory changes than it is to have order in memory changes. So that's an array. What about a linked list? Okay, well, what does a linked list look like? Well, we move our array up a little bit here. I can pull in a little figure of a linked list. So the idea of a linked list is that we keep track of the first element of the list, the head. What I've drawn here, this is technically a singly linked list. We'll see doubly linked lists a bit later. This first element is typically referred to as the head of the list, and it's a little memory chunk in here that stores the value that we want, as well as a reference to the next element in the list. These sets of boxes, these pairs here, are often referred to as nodes. So this is the first node in our list, this is the second node in our list, third, fourth, etc. Note that knowing about one node doesn't automatically tell you where everything is, whereas with my array, just a little bit of math could take me from knowing where the array is to knowing any element in it. With a linked list, if I want to know the 4th element, just knowing the first one doesn't help me. But the first one will give me the second one, and the second one will give me the third one, and the third one then can give me the 4th one. Okay, so when we want to go looking for things in linked lists, we have to jump around a lot. However, linked lists are much more efficient for doing the adding and removing, because let's say I wanted to add a new node, and I want to stick it here between, so this is index 0, index 1. I want to stick it at index 2, so it needs to go in here and push this down. In the array, if I were to do this, I would have actually had to come in and copy 2 values down. In the linked list, I don't have to do that. Turns out that if I can find this element, and that does generally require walking the list, so there is some slowdown here. But once I find this element, all I need to do is I make myself a new node, and I make it so that that node links in and points to there. Okay? And then I can point this down to here, and boom, I've now inserted this new element. So the amount of memory that I had to change, I had to get a new node, and then I did 1, 2 pointer changes in there. Okay. And this doesn't matter how big my list is. My list had 1,000,000 elements. The amount of memory that I would change is the same. So it's order 1 in memory alteration, but it requires us to walk through and find things in the list. Now over here at this end, I have a pointer that's labeled as tail. Okay, so this is a reference, this would be another variable that we could store. Not all implementations of a singly linked list need to store a tail. They all need a head. And note also these arrows are one-way arrows. So with the singly linked list, if you have this node, you can get to this node, but you can't walk backwards up these arrows. Also, because of that, you have to be careful of the way that you link things. When I created this list, if I had changed this pointer before I made this linkage here, note that now there is no connection to here. We would have lost it, and it goes away. The analogy I like to use with my students is you're floating in inner tubes down a river and you have ropes connecting the inner tubes, except these are really weird ropes because they're one-way ropes. And if you let go of the rope at the wrong time and you don't have a second rope in place, well, then there goes your ice chest with all the drinks in it, and it goes drifting down the river apart from you. So we have to be careful in how we do the pointers and make sure that we connect things in an order so that we always have links to the things we want to keep track of. The reason we would keep track of a tail, while it does add some extra work for a singly linked list, it turns out that the tail can make it much faster for certain operations. It is customary to have an operation that adds to the end, because in the case of the array-based list, it turns out adding to the end is the fast place to add. Adding to the beginning is slow. Well, in a singly linked list, adding to the end is only fast if you know the tail. If I know the tail and I want to add to the end, then I can simply make myself a new node and link it in, then change the tail pointer. Okay, and boom, we're done. So that's an introduction to the concept of what a linked list is, and hopefully you can see how it contrasts to an array and where they have relative strengths and weaknesses. The array is very good for finding things randomly, but it's not so good for inserting and removing. The linked list is bad for finding things randomly, but it's generally more efficient for adding and removing. So in the next video, we'll come back and we will actually write the code to implement our a list using this singly linked structure. We're not going to implement our list. We're actually going to go use something from the Scala libraries to do our implementation. But we'll see that next time.